Hello, so welcome again. As you can see, we have got an interesting circuit which is designed in real world electronics to develop some industrial applications. So, what you see on the screen, there is an operational amplifier. Positive input of it is connected to the ground, and to the negative pin, we have got input signal applied. Pin number 5 here is the output. Pin number 1 and 2 are the positive and the negative pins of an amplifier. Pin number 4 and 3 are VEE and VCC respectively, which is coming from these two supplies. VCC is set to 15 volt, VEE is set to minus 15 volt. You can see that these two capacitors C1 and C2 are there to reduce the transient noise when the first time power supplies are switched on. Now you see that the output from the pin 5, which is a VO connected here, is being fed back to the negative pin of the amplifier through the combination of the impedance composed due to resistor R1 and capacitor C3 here. And the input signal, so there is this negative feedback, what you see here, and the amplifier or operation amplifier is configured in a negative or in inverting mode. In an inverting mode, this amplifier is biased. What is there to the negative input pin? We see that the input is coming here, right from here. So you see that there is this signal source. Specifically, it's a current signal source. So this current source can be, as the designer chooses, can be configured as a DC current source, purely DC, or a time varying with an amplitude and the frequency, or for performing small signal analysis to obtain the frequency response of the overall circuit, you can configure it as a small signal AC source. Now, let's say when this is a pure DC current source, what that current may come from. So you see that such circuit is called as transimpedance amplifier or transresistance amplifier, or in a simple form, it is also called as current to voltage converter, because the input is the current and output is the voltage, and the ratio of output divided by input, which is voltage divided by current, is the gain, which is set by this resistor R1. So R1 is the gain of this circuit. Capacitor is there just to provide and provide the stability, and thus prevent circuit going into oscillation. So it's just there to provide the stability, and we would see it would act as a linear current to voltage converter with a gain given by the resistance. These are the power supply symbols we explained. Now look at this, where this current can come from. As I said, if this is configured as a pure DC source, where let's say I have a DC current of 100 nanoampere, this is full scale input current that can come from a sensor. For example, a photodiode can be modeled. Here is a model for the photodiode where the photodiode current can be modeled as a current source across which this capacitance is there. And this capacitance is from connected to the negative pin, to the pin input with respect to ground. So this capacitance one end is connected to the negative pin of the amplifier with respect to ground. So this is the input capacitance of the photodiode plus the differential capacitance of the amplifier, because the positive pin of the amplifier is grounded. So this capacitance is connected between these two pins. And part of this capacitance is some other parasitic. So you see, this is the total capacitance. And then the photodiode model also consists of this resistor, which is called as RSH or shunt resistance, which is there is usually very large. So there is some current that can flow through it also. So together, this is representing your photodiode, which can be a part of a portable system. This circuit also, together with this photodiode, can be embedded in a portable system. For example, high performance smoke detection system used in industrial application. So we know that when inside a chamber there is a smoke, there is a switching of the smoke alarm that indicates there is a smoke once the certain threshold is reached. So smoke, when there is a smoke in the chamber, photodiode, which is represented by this current source, can work, or in fact, it works on the principle of light transduction. So when light falls on it, photodiode conducts a current, and it works in a reverse bias mode. So it delivers a current as per the light intensity falling on it changes. So when there is enough smoke inside a chamber, light intensity falling on the photodiode will decrease. Accordingly, the current delivered by the photodiode will be modulated. Okay, so light is full on when there is no smoke, there is a current. When there is a smoke, with certain threshold, light intensity will decrease, and the photodiode current will get also increase or decrease based on the principle of the photoconduction. Okay, so this circuit together is an embedded application used in industrial smoke detection system. So now I have used this generalized operational amplifier from the library here. So I just click here, add symbol. Once I click here, I would type OP AMP, that is op-amp, and you see that I got this single node op-amp amplifier. This is like pin sequence. One is the positive pin, two is the negative pin, three is the output. You see that 1, 2, and in fact, output is the third pin, but here it seems 5, 4 is the V plus, or and 5 is the V minus. So there is some difference we see here, but nevertheless, we just say that how we used it. Then you just press escape button, double click here, and you see that there is a data sheet available. And the first pin is positive pin, second pin is negative pin, third pin is VCC. Now it is correct. Third pin is the VCCs. Yeah, right here. Pin 3 is VCC. Fourth pin is VEE, and 5 is the output. 5 is the output right here. Once that is done, you would like to click the simulation model. You see that this is general purpose op-amp in the KiCad. So pole frequency is set to open loop pole frequency is set to 20 by default, but you can set it as per your wish. Gain is set to 20,000 open loop gain. This is open loop pole frequency. In fact, this is offset voltage of 10 millivolt. You can choose and vary it accordingly. Let's say I want to set it to 1 millivolt. So this 1 millivolt will override this. Then the resistance R output resistance of the amplifier is just 10 ohms, so that it can have a capability to deliver full load current, a maximum source current. Now, once that is done, click the pin assignment. Here is the symbol pin, what you see in the schematic, and then there is a model pin, what we just read. So there should be a perfect mapping between and matching between symbol pins and model pins. So you see in symbol, pin number 1 is positive pin. So in model also pin number 1 is positive pin. Same, 2 is the negative in symbol, 2 is the negative pin in the model, and you can check other pins as well. Here you see some information about that amplifier. It is a generic model for single pole op-amp. Parameters are pole frequency, gain, offset, and the output resistance, as I just explained to you, and the values we can change. Then there is an author name here, Is it available as a public domain model? Output is limited to the supply voltage. So we've used plus minus 15. Now, how you call this in the sub-circuit? It is defined by the syntax sub-circuit, KiCad, built-in op-amp, positive pin, negative pin, VCC, VEE, and out. And then these parameters, what we just said, pole frequency, gain, offset, and our outlook. Offset is 10 millivolt by default. But now you can change that. Then those parameters have been modeled by means of voltage sources, dependent, resistance, capacitance, etc., etc. So then there is the output resistance that has been modeled and so many other information. Then it ends. So click OK. Once you click OK, you actually can click simulation model here. And you see now this is 1 millivolt, or here also you can change anything you want. So otherwise, what you need to do is if you have a manufacturer part of the amplifier, for example, op-amp 741, OPA series, LM series, we have covered numerous examples in our previous models. So if you want to know how to use the manufacturer provided spice model instead of general model, you can refer to our previous model where we have shown how to download download model in your computer, and then through this how you can call them here, then choose that model, and accordingly you can then go for mapping of the symbol pin and model pin, and then that would be your real operational amplifier instead of the generic model. Okay. Now, what you can do is I use 100 nano amp input current. I use resistance of 1 mega, and input current is applied here, and output voltage, in fact, is current multiplied by the resistance. So 100 nano amp multiplied by 100 mega should be around 100 millivolt at the DC analysis, right? 1 mega multiplied by 100 nano. I should expect 100 millivolt output. For that, to verify that, I need to perform an operating point analysis for the circuit. So before that, I will just save it. I would click ERC, click run ERC. I have 0 errors, 0 warning. Okay. I repeat again, you can use, instead of generic op-amp, you can just go and use any operation amplifier supplied by the manufacturer. And specifically, always search Google that operation amplifier for the smoke detector application. So manufacturers, different manufacturers across semiconductor industry will provide you those references in the Google search, that they will give you specific part of the op-amp that is dedicated to build a smoke detector application, in which you can configure the op-amp by the manufacturer as a transimpedance amplifier. Okay, that is perfectly suited for photodiode application we have considered. All right, so once that is done, we have seen no errors, no warnings. Go to simulator, and simulator is there now. Let me close this and click here, new analysis, operating point. So many analyses are there. So first I'll choose operating point analysis, then click OK. Once that is done, I want to click run. And look at this, my analysis is finished. It's completed in a very nice way. And I see now that what I see here, let me show you, because we have to interpret and understand the results very well. So let us scroll it up and read. So temperature, so 27 degree. So the analysis is done at room temperature. Now look at this, the current through capacitor, voltage source, etc. What we are interested in, we are interested in seeing the seeing the current I1, that is 100 nanoampere DC. Okay, the current through the resistor R1 is 100 nanoamp, close to that. And then we are interested in the output voltage of close to 100 millivolts. See, 98 millivolt, what we expected, right? And the power supplies are there. You can also see that if you use the real model of the amplifier, PXU2, let us see how much is the power consumption from the different parts here. So XU2 is about 7.9 nanowatt. Okay, let me just see that. Okay, so it's quite clear. Come back to schematic. You see now all voltages and currents are being highlighted, and at the output, we've got close to 100 millivolt, what we predicted, right? So 100 nanoamp DC from the photodiode gets converted into proportional 100 millivolt due to 1 mega resistance. And the offset voltage, let us see what the offset voltage of the op-amp will do. Now you chose 1 millivolt. How about I keep it 10 millivolt as it was. Click OK. Click OK here and see the impact of offset voltage, if any. So just save it. And the next step is to run the simulation. And you can see now the output voltage has been decreased to 88.999, right? Come back to schematic, look at this. So this is the impact of 10 millivolt, that's the input offset voltage. Okay, so you have to choose an offset voltage. The real op-amp, when you choose the manufacturer part, you have to choose to reduce this DC error in the output, you have to choose a op-amp which offers the least possible offset voltage. Similarly, you have to choose an op-amp which offers least bias current, because the bias current will also affect your output DC error. Okay, so what we can do is now change the value of a current. Let's say I use, instead of 100 nanoamp, I want to use, let's say 1000 nano. So it's about 1 micron. So 1 micron multiplied by 1. So it should be close to 1 volt. We'll see that if that comes. So click OK, click simulation, and we see the output voltage is 988 millivolt. So that's close to 1 volt. Okay. So in such, for a high level current of 1 micron, we can ignore the effect of offset voltage, but very small currents, that if your sensor current is pretty small and we want to actually detect those minute changes, look at the offset of the op-amp, the kind of role it plays, right? So that's it. So now once you see that R1 and C3 sets the pole frequency, right? You want to understand up to what frequency of this signal current the amplifier will perform the current to volt amplification in a linear way, right? And we can to verify that, we have to simulate its frequency response, where we can do the AC, small signal AC analysis. So let us do that. Let me just check here, click the new analysis, go for small signal AC analysis, click, let's say 1000 points, start frequency 1 hertz, stop frequency, let's say 10 megahertz. Click OK. Once that is done, click simulation. What are we interested in? We are interested in the output voltage gain and phase. So here, V of gain, click here. Now look at this, there's a little bit of instability sign, but it's okay. Gain is 120. The phase is like, let's say, change the color, green. Click on the green. Okay. Look at the phase is constant throughout up to is a 0 degree phase up to the frequency of, let's say, more than 2 kilohertz, and thereafter there is a 180-degree phase shift, and here it is that ringing. So uh, that is the AC simulation response for for your response of the circuit, because you have used 1 mega, right, and 3.2 picofarad. So all these parameters, C4, C3, R1, R2, are contributing you to your AC signal response. Okay. Now I want to see to what range the output is linear. I will just sweep the DC current range and see to what current range the amplifier is linear. So to do that, I click here, click the new analysis. I will go for a DC sweep, where sweep type is current. I want to sweep the current. Only current source I have. That's why I1 is shown. Starting value, let's say 0. Final value, let's say 1 microampere. Increment is, let's say, 1 or 10 nanoampere. And click OK. Simulate. Once the simulation is done, what am I interested in? I am interested in knowing the current from the I1 source, which is 0 to 1 microamp, linearly increasing. I am then interested in knowing the output voltage, and look at that. This is like a very good way. But if you zoom in this portion, I see that there is that zero current is here. Even though I don't have any current in the photodiode, I see a voltage of minus 10 millivolt. That's your offset voltage, right? Because the input offset voltage between the two terminals is 10 millivolt. And you got that at the output about minus 10 millivolt, right? So come back here. So that 10 millivolt is, even though I don't have a zero current, uh, I don't have any current in the circuit. So this is like open circuit, right? This is open circuit. This is also open at DC. And this 10 millivolt with respect to ground is appearing here, right? So correct me if you can. You are welcome to do that. What about I right click, fit on the screen? How about I want to increase the sweep range? So go from 0 to, let's say, 100 micro, but this is the generic op-amp, so it will support that sweep, right? So let's say, but if you use the real manufacturer part, that will be pretty. But no, we have modeled that op-amp with a specific volt frequency, limited pole frequency, limited gain, limited offset, and we limited output resistance. So we have put some conditions. It's not like that it will behave ideally. Look at that. The output is linearly increasing up to the current of about 15 micron. Thereafter, it saturates to the full scale supply voltage of 15 volt. So up to 15 uh, microamp, output is 15 volt, right? So for a 15 microampere, the output is going 15 volt, right? So the current is about 1 mega. The gain is 1 mega, which is the resistor, in fact. Here is the 1 mega resistance, okay? Now, exercise for you is to just get here, fill on the screen. You see that exercise for you is to design this high performance transimpedance amplifier for smoke detection application using manufacturer provided operation amplifier. Choose a part, search Google, which can be a best transimpedance amplifier for Photodiode application. Search with this frame, search with this phrase, or search transimpedance amplifier plus photodiode for search smoke detector. And then the manufacturer parts will be shown up to use that part use the spice model, map the symbol pins with the model pin correctly. We have shown in our previous model how to do that precisely. And with all that reference, simulate your results and put your answers in the comment sections, right? Now, and a second exercise, instead of configuring it a DC current source or AC small signal current source, now you can configure it as a time domain sinusoidal current source and simulate its performance for current to voltage conversion. Okay, so that was all for this model. Hope you liked it. If you did so, share it with others for a wider range. Stay tuned for more informative content like this. Till then, wish you happy learning.